Assalamualaikum and hello everyone. Welcome to our presentation for BMIP 2343 control system. I am Muhammad Afif Danial and today I am joined by my group mates Muhammad Syafiqka and Muhammad Akmal. We will be presenting our project on the system modeling and analysis of an auto cruise control system. To start, let's look at the overview of the auto cruise control or ACC system. When driving on the highway, maintaining a constant speed manually can be exhausting. The ACC is an automated system designed to maintain a specific speed set by the driver. In the real world, a vehicle constantly faces external disturbance such as wind resistance pushing against the car, or gravity components known as grade resistance when driving up a hill. The ACC system must continuously account for these variables to keep the tractive effort balanced and the car moving smoothly. The brain behind the operation is the proportional integral or PI controller. The PI controller's main job is to continuously calculate the error between the actual vehicle speed and the target set point that the driver has chosen. When an error is detected, for instance, if the car slows down while climbing a slope, the controller adjusts the mechanical outputs. Specifically, it changes the throttle valve position or the fuel injection rate. By doing this, it automatically increases engine power to compensate for the speed drop. Distractions allows a controlled slide, speed surge, or overshoot before the car stabilizes back at the target speed. Here we can see the closed-loop system architecture. This block diagram translates the physical vehicle dynamics into the Laplace domain, which allows us to perform mathematical analysis. The diagram maps the pathway for our reference input, RS, to the control output, CS. We have the error signal feeding into our pi controller block, which is represented by 2s plus 64 over s, and that feeds into the vehicle dynamics block, 1 over s plus 10, and finally a continuous feedback loop brings the output back to the start, driving the error margin towards 0. Next, I will pass the presentation to Syafiqka to explain the mathematical modeling.
Assalamualaikum, thank you Afif. Now let us dive into the transfer function derivation. First, we stabilize the feed-forward transfer function, GS, by multiplying the PA controller and the vehicle dynamic block together. This gives us GS equal to 2S plus 64 divided by S times S plus 10. Because this is closed loop system with unity feedback, we apply the closed loop formula to integrate the feedback pathway. This gives us our final loop transfer function TS equal to 2S plus 64 divided by S power of 2 plus 12S plus 64. With the transfer function stabilized, we can compare its denominator to standard second order characteristic equation. By isolation the term, we find the natural frequency by taking the square root of 64. Which give us 8 radian per second. Next, we calculate the damping ratio by equation to 12. Substituting our natural frequency of 8, we calculate our damping ratio to be 0.75. Using this parameter, we can calculate the theoretical transient performance of the system. For the peak time, we use the standard formula and find that the system reaching its initial maximum speed surge at 0.5937 seconds. For the settling time, the calculation show that the system stabilized at the target speed at 0.6667 seconds. Finally, the percent overshoot is calculated to be 2.84%. This is very low percentage, confirming that the system provide a smooth minimal speed surge. We also transform Laplace transfer function into modern state variable analysis. This gives us a metric format of x0 equal to ax plus bu and y equal to cx plus du. Based on our equation, metric A, which define internal system dynamic, is 0, 1, minus 64, minus 12. Matrix B, defining system input is 0, 1. Matrix C, defining output is 64 and 2. Finally, matrix D is exactly 0 because the highest power in our numerator is less than the higher power in the denominator. Okay, I will now pass it to Akmal to discuss the final result.
Thank you, Syafiqka. Let us move on into the S-plane stability verification. To determine if our system is safe, we evaluate the characteristic equation s squared plus 12s plus 64 equal to 0. Using the quadratic formula, this yields complex conjugate root at s equal to minus 6 plus minus 2 root of 7i. When plotted on the S-plane, both roots have a real part of minus 6. Because this real part is strictly located on the left-hand side of the S-plane, the system is mathematically confirmed to be strictly stable. Next is static error evaluation. Because there is single integrator in our feed-forward transfer function, this is classified as a type 1 system. When subjected to a step input, the system yields zero error, meaning it tracks a constant target speed perfectly. When subjected to a ramp input, which represents constant acceleration, the system yields a constant steady-state error of 0.15625. A parabolic input yields an infinite error, which is expected for type 1 system. To validate our math, we simulated the step response using MATLAB. This extraction from the MATLAB graph shows a peak time of 0.553 seconds, a settling time of 0.688 seconds, and a percent overshoot of 2.96%. When we compare this data to our theoretical calculation in the table, we see a minor deviation. This happens because standard formula assume a pure second order system without zeros. However, our specific closed-loop system contains a zero at s equal negative 32, which slightly alters the transient response. Finally, looking at our overall system reliability, we can draw three main conclusions. First, the PI controller effectively and safely managed the vehicle's speed. Second, the stability of the system is mathematically proven. The VIA left-hand S-plane pole placement. And third, despite the minor zero-induced deviation, our digital MATLAB simulation strongly validates our theoretical mathematical model. That concludes our presentation on the auto cruise control system. Thank you for watching.